Okay guys, this is it.
Hi guys, this is a Python notebook. In a little while I'm going to be describing this notebook in detail and going through the calculation and talking really about the method of the calculation. But I realized as I was describing it that I really owe you guys an explanation of how Python works and some of its ideas. So I thought it would be good to make a quick little video describing those basic features. So I'm going to make a new notebook, empty notebook. And then we'll just talk about some Python concepts. First of all, Python has variables, so you can define variables like a and b. You can simply assign them, and then I could say print a, and it would tell me what a is. I could say print b, it would tell me what b is. So you see that you can assign numbers to variables. You can also create things like lists. So you can say x is equal to a list, and then I could say print x, and it comes back with a list. And a list is nice because it can be indexed. So I could say, tell me the 0th thing in the list x, and it tells me it's a 1. What's the 1th thing? It tells me it's a 2, and so on. The other thing about a list is you can append to it. So I could say x append, and I could append a 42. And now x has a 42 appended to it. What is x? It's 1, 2, 3, and now it's got a 42. You can also do things like index the list. You can get pieces of the list. So say I wanted the list that is the x list from 1 to 2, like that. And that tells me that it's just a single element. That's called a slice. You could also do a similar thing. Let's say, what if I wanted from 1 to 3? That would give me 2 and 3. Now, the interesting thing about these slices is slice addressing is a little funny in that it starts at 0 would be the beginning, and then 1 is between the 1 and the 2, and 2 is between the 2 and the 3. 3 is between the 3 and the 42, and 4 is at the very end. So 1 to 3 is from here to here, and that means it includes 2 and 3. That's the idea. You can also slice from the end of the list, so like so. Or you could say that goes from the first one over to one from the end. If I append another thing to the list, let's say 12, and now we look at x, it's now got an extra element. Now 1 to minus 1 is the middle 3. It's from 1 to 1 from the end. So that would be 2, 3, and 42. Now the other thing you can do with lists is use them to drive loops. So I could say for I in x1 to minus 1, and then I could say print I. Now what that's going to do is iterate through this list that goes 2, 3, 42, and it should print out what it gets each time. So I is iterating through this list of things, and each time through the loop it's going to print what it sees. Let's execute that, and you see I got 2, 3, 42. If I just told it to iterate through x, it'll iterate through all of x, not just from 1 to minus 1, but the whole thing. And there's a special list generator called range. So if you say range 10, it creates a list that goes from 0 to 9. If I say range 110, oops, I didn't spell that right, 1 comma 10, come on, type, then it goes from 1 to 9. If I say 111, it goes from 1 to 10. Notice that it goes up to 1 less than the final number in the range. And there's also a concept of stride. If I add a stride to this, it tells me how many to skip each time. So this is the odd numbers, and of course I could do the even numbers this way, and so on. So those are some simple ideas. And finally, there's one last thing. There's the idea of an array. So if I tried to take, let's see, if I turn on PyLab, which is our graphing library, and that also includes a lot of mathematical functions like sine. So if I say sine of 0.5 or 0.4, it calculates the sine of 0.4. If I try to say what's the sine of x, it's going to probably fail. Actually, it's smarter than that. It converts it to an array and calculates the sign of all the elements. That's cool. I didn't even know it could do that. Okay, X is still a list, but it knows to convert it to an array. An array is, if I say X squared, it fails because it says this is a list and you can't really square it. But if I say array X squared, then it knows to take the square, it converts it to an array first. An array you can calculate you can do mathematical calculations on an array, and it just does the calculation for each element in the array. So for example, I could say y equals the array of x. It's going to convert x to an array. X is still a list, but y is an array constructed with that list. And so I can do things like y squared, or y plus 2 times y squared minus 3 times y cubed, and it's going to do the right thing. It'll calculate y plus y squared minus 3y cubed for each element in the array and can compute the appropriate number. So that's the difference between lists and arrays. That tells you how to do for loops. I think that's enough for one short introduction, but that should get us enough to understand the material we're going to introduce today. Okay, so I just wanted to point out that you can also open up a terminal in Windows and type IPython Notebook, and you'll probably want to set Chrome or Firefox to be your default browser because they work better with the Notebook, and that's also equally true on the Mac. Chrome and Firefox seem to be best, but you can see that you get a notebook, you can ask for a new notebook, and then you can jump in and start entering code, and the thing should work. So let's try it here. I could say x equals 1, 5, 3, whatever, and then I could say y equals array x. Oh, I forgot to say Pylab. I gotta get the Pylab stuff and then try it. Now I could say something like plot x comma y, and it'll do it. Of course, I didn't say inline for Pylab, so it's going to run, let's see, there it is. It's going to run in an external window, but that's also nice sometimes because then you can do stuff like zoom and so on. So that's the way it works. All right, it's time for Euler's method, or integrating coupled differential equations. So why do we want to do it? Well, Euler's method is a technique that we're going to use to estimate solutions to first-order differential equations. Now, you say, well, what about second order? Well, it turns out second-order equations can often be recast as coupled first-order equations. So if we can figure out a general plan for finding solutions to first-order equations, then we can just use a coupled variation of that to find solutions of higher-order equations. So that's the bottom line. But why do we want to do that? I guess that's the next question. And the answer is that laws of nature are very often described as coupled first-order differential equations. So things like Newton's laws, things like relationships between energy and time and space, and laws that have to do with thermodynamics, laws that have to do with electricity and magnetism, and so on. So suffice it to say that the universe is rich in relationships that are most easily expressed in terms of differential equations, and so it's extremely important that we understand how to handle those. And the other reason why we're interested in Euler's method is because it's the easiest, it's the most simple, straightforward, least complicated technique. So it's a good place to start. All right, so how does it work? The idea is this. You imagine you have some system, and the system can be completely described at any moment in time as a state S. In other words, if you know S, then you know everything there is to know to tell what the system is doing at that moment in time. So, for example, if we're talking about a particle, if we knew its position and its momentum at any given time, then we would know everything there was to know to predict about its future evolution, assuming we know something about the forces that are acting on the particle. Or if we have a system of particles like the planets going around the sun, then if we knew the position and momentum of every single planet, every single object in the system, and we know how they interact with one another, we can use that with Newton's second law in order to cook up a relationship that tells us how the thing goes. But at any moment in time, in order to get it started, we need to know how things are now, which means we need the position and momentum of each particle. So the state would be the position and momentum of each particle. And understand that the position could be a vector, so it could have 3 components, and the momentum could be a vector, so it could have 3 components. So that could be a 6 components, 6 numbers for every object, and there could be 9 planets or 12 particles or whatever, and each of them would need 6 numbers. So the state can be a fairly complicated thing. It could have a lot of pieces, but it's still, we call it S, it's the state. And it tells us what we need to know what the system is doing. The concept is that you have some rule that allows you to predict what's going to happen next. And so that rule you express like this, and it basically says the rate of change of S is equal to some function that depends on S and time. So that's the idea. So if we have a rule like this, and we know the state of the system now, basically, Euler's method is a way of using that information to predict what's going to happen later. How do we do it? We simply write down that the change in S divided by the change in time is approximately equal to the derivative of S with respect to time, which we already know is given by the rule. So we approximate ds dt as a finite change in S divided by a finite change in time. And then we simply solve that for the change in S. So if we know the rule f of S and t, and we know how long that rule is in place, a short period of time, that's going to equal the change in the state. And the change in the state tells us what the new state is going to be, because if we know the state now and we know how much the state changes, then we can calculate the new state. So that's it. That's basically all there is to it. It's actually quite simple. The new state is the old state plus the change in S. And you can think of it graphically this way. F of S and t is just a function that tells us the slope of S as a function of t. And if we know S now, then we can predict what S is going to do in the future. Now, clearly, what we're doing here is extrapolating. So we're taking the slope of S as a function of time now, and we're assuming that the slope doesn't change very much as long as we take a small change in time. And obviously, you can see from the picture that that's going to introduce some amount of error. But if delta t is small, and if the slope of S is relatively constant over the small time interval, then it could be a good approximation. So let's look at an example and see how that works. So radioactive decay is a very simple physical situation, and basically it obeys the rule that the rate at which the number of nuclei, the number of radioactive nuclei changes, is proportional to the number of radioactive nuclei that there are at a given moment in time. So, for example, let's say that we have 100 radioactive nuclei at t equals 0, and we have a rate, lambda, that says 1 decay per second per 100 nuclei. In other words, 0.01 decays per second per nucleon, I guess is how you'd say it. So another way to think of that is that there's 1 decay per second per 100 nuclei, or 1 decay per 100 seconds per nucleon. Anyway, after 10 seconds, how many nuclei do you expect to remain? So you start with 100, you have a rate of 0.01. So the idea is you simply multiply 0.01 by the number of nuclei right now. That's 100, and you end up with 1 nucleon per second decay rate. In other words, you're going to lose 1 nucleon per second if you have 100 right now. And if you wait around for 10 seconds, losing nuclei at a rate of 1 per second, you're going to lose 10. So that means you're going to start with 100, you're going to lose 10, you should have approximately 90 remaining at the end of the time interval. Notice that this assumes that the number of nuclei doesn't change in the 10-second interval. But in fact, we know that it's going to go down by 1 after 1 second, and down by another 1 after another second. And so you can already see that you can improve the accuracy by reducing the time interval. Do 10 iterations of 1 second apiece instead of 1 iteration at 10 seconds. But you get the idea. So what I want to do now is to go through some demos to show you how we're going to use different kinds of approaches to actually see how this thing works. Okay, so here we are at the command prompt on my Mac. Now, once you get the software installed, I find the easiest way for me to launch things is in the command prompt, and I'll show in a minute how you can also do this in Windows. But basically what you do is you type IPython notebook. First you get yourself in the directory where your stuff is. In this case, my directory happens to be it's in the documents, docs, UI stuff, math methods 1, NBS. So it's just a directory where I have stuff. NBS stands for notebooks. In this directory, I just happen to have one notebook that I've already started. In fact, I uploaded this notebook to the web server for the course, the ACE web server, so you can grab it there. But anyway, you run IPython notebook, and it opens up a web browser with the list of all the notebooks in that directory. So here's the directory again. Notice NBS at the end there. And Euler intro was the same Euler intro that was listed in that directory as a notebook. So that just shows you what's there. If I click on the notebook, it opens it up. And you'll notice that this notebook format is nice because I can type in, when you type, it looks like this. This is, I just double clicked on that cell and you can see what it looks like when you type it. You use LaTeX-like notation in order to do math. And you use stars and underscores, there's some underscores here, and so on in order to notate the thing. It's a notation called Markdown. And you can read about Markdown and how it works on the web if you do something like you Google Markdown syntax. There you have it, Markdown syntax. You can see there are websites where Markdown syntax is described. It's basically, it's pretty easy. If you want to make a header, you use underlines. If you want to do different heights of header, you use pound signs. If you want to do, let's see, what else is there? You can use stars and pluses and minuses to make lists. You can use like double star to make bold and single star to make italics. Anyway, have a look at it, and if you have questions, let me know. But basically, it's nice because you can embed nice-looking documentation with your code. So one of the problems with most code development systems is they're great for doing code. They're not so great for doing documentation. So this is nice because you can kind of mix the two together. Here's a little, this is basically the same stuff I just talked about in the slides. So in fact, it's verbatim, exactly what was in the slides. It's also in the notebook that's on ACE, so you can download it and read it there as well. Here's a little Python program that does the calculation of the decay using 1 second, excuse me, 1 second time steps instead of a 10-second time step, and it does it over and over again. You'll notice it gets about the same answer. It got 90.44 instead of 90, so it's a little bit more accurate. But what I want to do is talk a little bit about the syntax here, and point out another feature of the notebook. Another feature of the notebook is that you can put in Python code and execute it within the notebook, and you'll see the results within the notebook. And so there are variables here. Lam stands for lambda. The actual word lambda written out in English is a reserved word in Python. It means something special, so we can't use that as a variable name. But lam is short for lambda, and dt is the change in time. S is the current state, which in this case is the number of nuclei at this time. And we're going to start t out at 0. And then what I just printed a string which says t and s in order to make this column header. And then we're going to have a little loop here. So for I in range 11 means I goes from 0 to 10. So it's actually going to go through 10 steps. And what this thing does, it's 11 steps, excuse me. What this thing does is it prints out the time and the state. It adds minus lambda times s times dt to the current state, and then it adds dt to time. So, and then it just repeats that over and over again. So let me, actually this is no different than s equals s minus lam times s times dt, and t equals t plus dt. The plus equals means the same thing that I just wrote here. It means t becomes t plus dt, s becomes s minus lambda s times dt. And if I execute, you can execute code by simply holding down the shift key and pressing enter while the cursor's in a cell, and it'll go out and execute that, and you can see it didn't change anything. It still got the same result. And we can also turn on graphing. PyLab, for those of you who are familiar with MATLAB, PyLab is a graphing environment that's a little bit like MATLAB. It includes all the matrix stuff and so on, but also the graphing. And inline means we'd like to see the graph in line with the code. So that enables us to see the graph down here. So, and basically all we're doing here is taking the same code, but adding enough record keeping so that we can graph the results. And so I make an empty list called slist and an empty list called tlist. Slist and tlist are empty lists because I'm assigning them to open bracket, close bracket, which is just a notation that means an empty list, a list with nothing in it. I start the variables lam, dt, s, and t out the same way I did before. Now what I want to do is to start out with the tlist appending the current time and the current state. Then I just repeat the same exact process, except every time through the loop I'm going to append the current time and append the current state. So when I'm done, I'll tell you what, I'll change this so it doesn't plot, but instead it prints tlist and it prints slist, so you can see what it looks like. So here is the tlist. I'll do it this way. Print tlist equals and tlist, and then we'll print excuse me, slist equals slist, and you can see tlist is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Slist is equal to 100, 99, 98, and so on, down to 90.43. So we actually are going a little beyond before we printed before the change. Now we're appending after the change, and so we get an extra time, an extra s at the end here. And then we can also plot those. So I can say plot tlist, slist, and let's make it with blue dots. And that's interesting. Oh, I forgot to execute this. And there it is, blue dots. And notice it goes down to about a little below 90, which corresponds to this 89.53 here. We can also put in the exact result. The exact result, of course, is tlist. It's going to be 100 times e to the minus lam times array tlist. Let's do that. Oh, and I need to make that with let's make that one with a red line. And you can see there, now this is the exact solution. This is the computed Euler method solution, and you can see they're actually quite close. In class, we're going to go through and see how this exact solution comes about. If you're not familiar with it, it's quite easy, and you can see the result.
And that's pretty much all there is to it. We'll see you guys next time.